Yeah, hello. So now let's continue with more on data visualization of quantitative variable, okay? Now we'll be looking at correlations, okay? So this will be a continuity of what part one of this data visualization of quantitative variable. So first of all, let us load our data set. So let's get our data set by using the read.csv. We are getting our hints data again. And we are using two different data sets, which is the hints data and then the biomass data. So let's look at, so we have this, our hints data. Let's select it. So now, again, you can actually find this particular, the code for this presentation, or here you can actually copy, paste, and then learn along, okay? Okay, all right. So let's pull it up. Okay, so now we have our data ready. So we can look at the names. We can look at the names on the data. We can actually be able to observe the summary, okay? And then now we can be able to, let's attach the data, okay? So that we wouldn't always use the $ to pull a particular variable. So we attach the data. Now this red shows that the several data have been attached in the past. So usually what you can do is once you are done, you can detach it. Okay. So now let us clean the data by removing all the negatives we have in the data. You can see we have some negatives. So there are some variables we would want to analyze. So we would want to get rid of all the negatives. So let's try to get rid of all those negatives. And then, so by going into the data again using the concatenate function, telling R we want every data that is greater than 0. Now R is able to eliminate any of those data, okay? And then bringing the comma sign here, we still want you to retain all the columns of the data. Okay, so now you can go ahead and run the summary, and then you can see those variables we chose. There are no negatives within those variables. So which means for now we are good to perform some analysis, okay? So we can go ahead and attach the new data we created from the old data, which is now the clean data, which is the hints data new. We can attach that data, okay? So again, don't worry about this red because there have been several data which have been attached, so we can detach it in the future. Now we can look at the dimension of this, which is giving us what? 2,738 by 17 columns, okay, which is the number of observation is 2,738 and the number of columns is 17. Okay, so now we would want to actually visualize some correlation and some scatter plot, okay? So another data we are going to make use of is what is called the biomass data, okay? So I would want you to again also load that data set. So which is the biomass data. So now that data should now be available. We can also attach that data set, and then we can look at the names of it. It is having about 28 columns, and then we can actually look at the head of the data, which is the first 6 observation. So now let us look at what is called the scatterplot metrics, okay? So assuming we want to observe some scatterplot metrics from this particular data where we are choosing only the quantitative continuous variable, right? Remember, whenever you are performing scatterplot, it has to be, the variables have to be continuous, right? Unless within the plot you actually want to indicate some categories, then you have to include a categorical variable. But in the meantime, we want to observe only the continuous variable. So we are choosing column from 4 to 8, okay? So within our biomass data, so we say plot biomass underscore data of this particular variables, which is column 4 to 8. So with the square bracket, comma, give us all the observation So you are plotting for all the observation from column 4 to 8. And there's the PCH style, which is the point style we want to observe. And there's the we have the sex, which is 1.5, which is also going to give us how we would actually want to observe, some of the panels. And then we have the color, which we have it to be a steel blue. Okay, so let us run this. Okay, so now you can actually see. So there's the observation of the scatter plot of column 4 to column 8. So we have column 4 is REP, 5 is LFBM, 6 is STBM, 7 is RTBM, and then 8 is what? LFNCC. Okay. So with this scatter plot, the way in which you read it, and the fact that now we are able to actually, for this particular panel over here, it allows you to observe the relationship between RP, REP, and then LFBM. This here allows you to observe the relationship between REP and STBM, which is this panel. This panel here, again, this panel shows the REP. And then for each of them, you are able to observe the relationship with the other variables, okay? So for instance, this last one here is the relation between the REP and then LFNCC, which is this particular panel right here, okay? Now, if you move forward again, we have right here represent all the REP, and then for each of them, you're able to, so this panel here is REP and then LFBM relationship, okay? This right here is relationship between LFBM and then STBM. Okay, so this panel, they are showing the same relationship, which is the LFBM and then STBM, okay? And so on and so forth. So this is how we are able, so you can see that between the LFBM and then STBM, you can see their relationship, they are giving some kind of strong positive relationship, okay? Yeah, and then over here, for REP and then LFBM, we are not able to actually observe any kind of good relationship between them, okay? And then you can see some of the variables have been, clustered. So maybe you might be thinking about, could there be some cluster between these two variables? That's something to observe in the future. Okay, so that's the interpretation you can actually observe and how you can read this metrics, okay, for each of those variables, observing their relationship. Now we can use what is called the pairs function. Rather than using the plot function, we can use the pairs function to also observe the relationship. So for instance, if you want to observe the relationship between some variables within the our clean hints data, okay, and those variables we are looking at is variable 5. So I can actually pull up the names. So names of the hints, new data, okay. So we are looking at the relationship, the metric really correlation matrix relationship for variable 5, which is age, variable 14. So 14 is BMI, 16 is weekly exercise, and then the 17 is what is the number of drinks per week, and they are all continuous variable, okay? So now we use the pairs function. Again, within a square bracket, we said that we want all the observations, so comma, then we choose our columns in which we would want to observe that relationships. Okay, so now here we have, so this showing, so this right here, the relationship between age and BMI, this right here, the relationship between age and weekly moderate exercise, this right here, the relationship between age and average drink per week. Again, this right here is the relationship, looking at the relation between BMI and age. This is BMI and weekly average, that weekly minutes moderate exercise, and this right here, BMI, and then what? Average drink per week. Okay, so now what we can actually do is we can decide to exclude the lower panel, okay? So maybe, I mean, the lower panel and then the upper panel, we are able to assess the same relationship. So instead, we would want to exclude the lower panel so that we can focus on only the upper panel and then be able to clearly explain our relationship, okay? So in this case, you can actually, within the pairs function, you can introduce what is called lower dot panel equal null, which means we don't want the lower panel to appear. So if you run it, so you can see the lower panel. Now, if you go back, we have the lower panel, but if we go forward, we are able to eliminate the lower panel. Now we can access age and BMI, age and weekly moderate exercise, age, and then average drink per week, okay? And then you are able to understand. I mean, it's so hard for you to explain the relationship what is happening. They are all they have a very weak relationship between each other, okay? Yeah, so another thing in which you can actually do is also we can actually introduce color, okay? So within this particular panel, okay, we might want to also observe that this relationship and to be able to identify gender within this relationship. So for instance, if we have a relationship between age and BMI, what is the case of the gender, okay, within age and BMI? What does that relationship actually, look like? So we are able to identify gender within this relationship, which is male and female, okay? So the way in which we do it is, again, we use the pair function, we select our data for the relationship. We want the PCH, which is the points style, to be 19. And we are using the color. We are choosing a color of what? Rainbow. So we want 2 colors from the rainbow. But then we want you to use that to identify gender within our data set. So it is going to identify gender within the relationships we have among these variables, okay? Again, we want you to exclude the lower panel. Okay, so we say lower dot panel equal null. Let's run that line of code. Okay, so now we can enlarge it and see. So now over here, you can actually observe. If you want to zoom, you can actually use the zoom function to be able to even look at it very well, okay? And then to be able to observe the relationship. Now we can see the different colors in which we actually have, and those different colors is representing the color of male and female within the data set, which is the gender, okay? Now, if you want to actually make use of this particular plot for your, let's say, project, you can just hit on right click and then copy the image and paste it in Word. Or you can use a sniping tool to just snipe the image and then you can paste it in Word, okay? Okay, so now, next let us look at several other ways in which we can actually assess this correlation. So we have what is called the psych package. The psych package allow you to also observe different style of correlation, okay? And you have to first of all install the psych package if you haven't already installed it. And once you have installed it, you have to load it. So I have already installed it, so I just have to load it. So now the psych package allow you to use a function called the pairs.panels function. And that is actually going to give you again correlation matrix, just like, we did for the plot, but in a different way in which you can actually, observe several different way to analyze your correlation data. Okay, so let's run it. So now, this right here, not only are we able to observe the relationship, the distribution of the variables, so the center give it the distribution of the variables. So you can see that this one looks more like the rep looks more like a categorical variable. And this one, it looks fairly maybe normal. This one is a little bit right skewed. This is a little bit right skewed. This is also fairly normal or a little bit right skewed. But then we are able to observe the correlation coefficient. Remember, correlation coefficient is between -1 and 1, right? If -1 means absolute, we have -1 means the strongest negative relationship, right? And +1 means we have the strongest positive relationship, right? But then the higher the positive, the higher it tells you the positive relationship, and then the lower the negative, it tells you the lower relationship, negative relationship. So for instance, if you want to look at the coefficient for rep and then the other variables, for rep and then LFBM, we have 0.03. Rep and then STBM, we have -0.07. Rep and RTBM, we have -0.04. And then rep and LF and CC, we have 0.23. So with 0.03, it is having weak positive correlation or relationship, right? Over here, we have weak negative relationship between rep and then STBM. The same between rep and then RTBM, we have weak negative relationship. And then between rep and then LF, NCC, it's kind of close to moderate relationship, right? Okay, so this is how you can, and then these are their scatter plots in which you can also be able to observe the scatter plots. So the lower panel give you the scatter plots, okay, with some smooth through it. And then the upper plot give you the correlation coefficient. And then the middle plot give you the distribution of the variable. Okay. So now for our hints data, we can do the same thing, okay, where we use the panel and then we're able to observe the relationship and then the correlation, okay? So let's look at it. Okay, so now you can see that, and then we are also able to give it a name, okay? So we introduce the title of our plot to do our distribution, scatter plot, and what correlation. Okay, again, make sure you always give a meaningful, something meaningful in terms of your titles. Okay, so now we are able to observe the relationship between age and BMI. You can see 0.01, which is very, very weak positive relationship. Age and then weekly moderate exercise, -0.07, which is also very weak negative relationship or correlation. And age and then average drink per week, which is also -0.03, which is also negative, weak negative relationship. Okay. And this is actually observed. If you look at their scatter plot, which is the lower panel, you can see the scatter plot between this relationship. And then you can see the middle panel, which is showing their distribution. So the distribution of age is fairly normal. The distribution of BMI is kind of right skewed. The distribution of weekly minute moderate exercise is also very right skewed. And distribution of average drink per week is also very right skewed. And sometimes some of these relationships, the way in which they are weak may be influenced by outliers. So to move forward with further analysis, the best you can do is sometimes to remove the outliers to ensure that you get the accurate relationship between those variables, okay? But that's not what we are doing now. Over here, we are just displaying and understanding these plots. Now, there's also a way in which you can also show some correlation plots using heat maps. So we are going to use a package called the core plot package, okay? again, you have to first install it if you don't have it already. Once you have installed it, you can actually load it or activate it. I have already installed it, so I have to load it. Now, before you use the core plot to show any correlation plots, first of all, we have to create our correlation or obtain our correlations. And the way we obtain our correlation, we are creating our correlation metrics. And then we say that core of biomass data. So the biomass data, we need the correlation from 5 to 8. Okay, we are looking at the variable column 5 to 8. We want you to give us the correlations for those variables. Okay, and then store it in core EED. Okay, so let's run it. So, okay, so we've run it. So once we have run it, now we can go ahead and use the core plot function to be able to show our heat maps, okay, for to assess the relationship between these variables from 5 to 8 of our biomass data. Okay, so now within the core plot function, we bring in the correlation matrix we actually created, which we store it in the core EED. We put it in here, and the method in which we want to use it, what? The number method. Now, within the core plot function, it is having so many different methods in which you can actually use to display so many different type of, correlation between the variables. So let us use, first of all, look at the number method, okay? So here the number method in which we are able to actually observe, okay? So let's put it here. So now we are able to, so in the middle, it's assessing, in the middle, you see that we have 1.00, 1.00, which means a perfect correlation. And a perfect correlation, because it is actually pairing the variable by itself. And if you correlate a variable by itself, it gives you a perfect correlation. So over here, we have a perfect correlation. Here, perfect correlation, which is looking at STB, STB, RTBM, RTBM. So all the middle of the correlation matrix is 1 because it's representing what? A perfect correlation, which is a correlation of the same variable with itself. But then moving away from there, if you look at right here, now the deeper the color, the more, if the color become more thick blue, it means that it become more highly positively correlated, right? And if it become thick brown, the more it approaches the thick brown, it tells you the more and more it become highly negative correlated, okay? So you can be able to, and then those, when it is light blue, then it tells you that maybe there is a positive correlation, but the correlation is kind of weak, okay? So find that the correlation between LFBM and then STBM for the biomass data is what? 0.91, which means a very high positive correlation or relationship between these two variables. Now for LFBM and then RTBM, it shows 0.353, which is less than the relationship that was observed between the LFBM and then STBM. So this one is actually looking at more of maybe moderate kind of correlation. Yeah. And this one right here, there's a weak negative correlation between LFBM and then LFNCC. Okay. Yeah. Okay, so you can actually also use a different style, which we can actually look at. We can use a method called the color method, and then we can order it in alphabetical order, okay? So within the core plot function, again, there's our correlation matrix we created. We are using a method which is called the color method, and then we are ordering it, okay? Let's plot. So this is how we have it. So this right here is again the dark blue color is telling you a perfect correlation, and that means the variable being correlated with itself. And then also, so the thicker the blue color, it means it become more highly correlated. And then the lighter it become more the correlation reduces, okay? And then also the same way the brown color, the thicker the brown color become more highly correlated, and if highly negatively correlated, and if the brown color reduces, then it become the correlation become weaker and weaker as the brown color reduces in terms of the negative relationship between those variables. Okay. Now, similarly, we can by default, if we don't introduce any method, but then we just use the call plot function to display our correlation metrics, this is what we observe. We are also going to observe some circles, which is again explaining the same thing in which I did explain. The thicker the dark blue color shows a highly positively correlated, and the dark brown color, the darker the brown color becomes, it shows a highly negative correlation. So you can see this right here is showing a negative correlation between LFC, NCC, and then these other variables, okay? So another method in which you can also have is the ellipse method, okay? The ellipse method in which we can also have an order of AOE, and then we can have it to be the type to be what? The upper panel, okay? So again, we can plot it, and then let's see. Okay, let's run it. Okay, so this one right here. Yeah, even before we go to this ellipse method, this one right here also gives us a different kind of correlation plot, okay, with a different order as compared to what initially we have over here. This time around, it have been able to put them in the form of an order. Oops. Okay, so now if you want to see an ellipse, this is how we actually display an ellipse sign. Again, these lines in which you are actually seeing is telling you perfect correlation because the variable is correlated with itself. And this one, yeah, now the closer the ellipse is, the more highly correlated it is. So there is a very high correlation between LFBM and then what? That's LFBM and then STBM, okay, which was actually observed over here. So you can see LFBM and then STBM, the correlation is 0.91, right? And that can be observed from this particular ellipse over here, right? Okay. So these are different correlations in which we can actually plot, okay? So now let us look at if you have a data file, okay? We want to further look at more on this correlation. Now we have a data file. Let's create our own data file, which is data which was inputted over here. So first of all, we have to first run the data. Let's run the entire data. Okay. So now the entire data have been run. So this is the data we have. So to make use of the data, we are actually going to call the data lizard, okay? It's kind of a lizard data, okay? And we are going to be able to read from this table. So we are using read.table, which allows us to read the data file, okay? So within the read.table function, we are going to have my.data file with header equal false, okay? And then we are going to actually introduce our own header name because it doesn't have header, but we are now giving it header. So we have the column names, call.names equal mass, SVL, and then HLS, okay, and then gender. So those are the column names for this particular data. So by running this line of code, it's actually able to create the data frame of this data set for us. So first of all, we can attach the data, and then we can look at the names of the data. So these are the names of the data. And then you can even look at the head of the data. So we have the mass, SVLS, SVL, HLS, and then gender. Okay. Now look, using the pairs function, we know the first three variables are continuous variables. So we can use the pairs function to generate the correlation metrics for those variables. Okay. So we can see the correlation. The correlation look they have kind of strong positive correlation between these variables, right? So again, we can use the pairs function, and then we can actually make it more prettier, right? So the pairs of the lizard data of the first three variables, we have the point style to be what? We're using the PCH to be 19, and we want to actually also identify gender within this relationship, okay? So we know that gender is male and female, but we are using a rainbow color of 2 colors from the rainbow to be able to identify the gender within this relationship, okay? And we are going to name it, we are going to give it a title of scatterplot metrics of mass versus SVL, and then also versus HLS by gender. Again, you can just also say relationship between these 3 variables by gender, okay? So again, always give your plot a meaningful title. There's not meaningful enough, okay? Okay, so if you look at the relationship between mass, SVL, and then HLS, we are able to observe them. And then now we are able to see the gender within these, variables, right? For instance, if you look at mass and then SVL, you can actually see that the female gender, which is denoted by the blue color, is actually almost at the top here, right? As compared to, so you can say there is a high values of a relationship between mass and SVL for this blue color as compared to the red color, okay? Now, you can actually use, we can plot a scatter plot, a 3D scatter plot, okay, which is more of a very advanced scatter plot you would want to plot for these 3 variables, okay? So to do that, you actually install this package, which is the Scatterplot 3D, okay, and then you load it. So I've already installed it, so I just have to load it. And then now we want to actually observe the scatterplot. Okay, so this line of the code, remember, only allow us to be if we want just a single panel. So we are already having a single panel, so we just have to maintain it. We don't have to rerun it. Now let us look at the scatterplot, 3D scatterplot. Okay, so now we are able to observe, and this is what a 3D scatterplot of this the 3 variables. Okay, so we have mass, SVL, and then also HLS, and then you can see that between these 3 plots, they are showing a positive correlation and more strong positive correlation between these 3 plots. Okay. Now, next, we can also be able to now identify the gender within the plots, okay, within this 3D plot. We can identify the gender within the 3D plot. And to do that, we'll go into our lizard data. Okay, we are creating another column for the data, whereby we said we are creating the column, and for every gender equals to F, which is female, we are denoting it by red color, okay? And then we are creating, again, the new column is going to be P color, going into our lizard data for gender equal M, replace it with what? Blue color, okay? So now let us run this line of code. So we run this line of code. So now with that, we can be able to even look at the head of this lizard data. Okay, let's look at the head of the data. So now you can see now the data have included what? P color, which was a new column we actually created, okay? So now we can now go ahead and then plot our 3D plot for these variables, which is SVL, HLS, and then mass. And then for the color style, we are going to choose the color in which we created for the new column. So the color, go into the lizard data and then choose this color, which is the P color. Again, we are maintaining we are giving a plot, the points, the style of the points to be what? PCH, which is goes to 90, which will give us a more deeper, not a circle, open circle, okay? And then now this is the name in which we are actually giving it, okay? 3D plot of SVL versus HLS versus mass, okay? So now let's go ahead and plot and run it. So now we are able to identify the 3D, and then we can actually observe it, okay? So we have the male represent blue, and then you can see that male have higher values compared to what the females, if you look at the relationship between these variables, okay? Because you can see the blue color, and then of course the relationship looks there's a strong positive relationship between these three variables with males having higher values, okay? Now, we can also be able to have a more interactive plot. And to have that more interactive plot, we are going to use a package called the RGM, okay? And then you have to install it and then you load it. So I have already installed it, so I just loaded it. Now we want to see an interactive plot so that to be able to move the plot, okay, interactively and better understand how does the relationship and the distribution of gender among these three variables look like within a 3D plot. Let's run it. Okay, so now we have it here. We can open it, and now we can actually rotate our plot to see that, oh, okay, so these are plots in which we can actually, observe to see the relationship between these three variables, okay? So depending on how you actually want to observe the relationship, you can actually continue to rotate this, okay? Okay, so I think we ended with the fun stuff. Now you're able to get a 3D plot, which is very interactive to understand how your relationship between three plots, three different variables, which are quantitative, looks like. So I will see you in another presentation with the more fun stuff when it comes to visualization.